In our previous video, we took a look at acid halides, and we said that they're quite reactive with a wide variety of nucleophiles because the chloride on there, or bromide, is such a good leaving group. What I want to do today is I want to take a look at the next most reactive species, the anhydrides. And luckily, the reactions are going to be very, very similar for the most part, so we're not going to learn a lot of new reactions, but there are subtle differences. So let's jump straight in. So let's take a look at how we prepare anhydrides. And luckily, it's pretty straightforward. And I wanted to start out with the simple ones. And the simple ones only work for small, unfunctionalized anhydrides. Let me zoom out a bit. And what I mean by this is what's done for the industrial preparation of, let's say, commercial reagents. So, for example, if you have a small carboxylic acid, you can actually just heat the reaction up to 800 degrees Celsius, and you can get these to couple together to form symmetric anhydrides. So it'll always be symmetric. As you can imagine, running a reaction at 800 degrees presents its own unique challenges too. So really, you can't do this with starting materials that can fall apart. However, if you have something like acetic acid, you could react acetic acid, where this R group is just a methyl group, into something like acetic anhydride by reacting it at 800 degrees Celsius in a specialized vessel. But for most lab conditions, this is not something that we're ever going to see done. All right, more elegant way / more complex way is just to make an anhydride directly from an acid halide. So let's take a look at the more complex method. In general, acid halides are the king of all carboxylic acid derivatives, right? We can make just about anything from an acid halide. So all we really need to do here is to have some sort of carboxylate salt. So if you remember, a carboxylate is defined by having a negative charge, meaning we've deprotonated a carboxylic acid using some simple base. And then we just need our acid halide. And as you can imagine, this negative charge can attack in, kick up electrons. We would get a negative charge on that oxygen. And then in our next step, we can just kick off chloride as our leaving group. And by doing this, we no longer need to worry about running the reaction at a really hot temperature. This can be unsymmetric, it could be symmetric, and it can be run at low or moderate temperatures. So let's make a list of the pros here. Can be run at low T, meaning low temperature. Can be used to make unsymmetric anhydrides. And then the other benefit of this is you don't really need to worry about adding anything else, right? You don't need to add pyridine, you don't need to add any other sort of special reagents. So this more complex method is oftentimes preferred, especially in a lab setting, because it's quick, it's easy, it can be run at low temperatures. There's really no fuss with making it. All right, let's take a look at this chemistry in a practical context. So let's take a look at practical applications. And a lot of these are relevant to those of you that are looking at going into something like pharmacy or medicine. The first one's pretty interesting, and that is we can take this starting material that's a benzoic acid derivative, but it's got an alcohol coming off of that ortho position. This is referred to as salicylic acid. It's a commonly available starting material. And we can react this with an anhydride. Specifically, this is the anhydride of acetic acid. So this is acetic anhydride. And when you react acetic anhydride with a alcohol, so for example, we've got an alcohol coming off here, you can imagine that this alcohol will attack in and kick up electrons. We'll have some proton transfers. In fact, let's even just show the whole mechanism. So after this step, we now have an oxygen with a negative charge. And this oxygen with the negative charge can then clamp down, can kick off electrons, and basically treat this entire group over here as our leaving group. So we're not quite done yet. We still have this oxygen with a positive charge. And our leaving group, when it was kicked off, has this negative charge. So this will come, grab that proton, and as you can see, we'll be able to form a new ester. And in this case, this leaving group essentially acts as our base, and we'll get a carboxylic acid byproduct. Well, what we've made down here is aspirin. And the neat thing with aspirin is that this entire group over here is called an acyl group. And acyl groups are often just abbreviated as AC in biochemistry. And what aspirin does is it will transfer this acyl group to an enzyme that causes inflammation, basically blocking the inflammation pathway. But this acyl group is installed by using acetic anhydride with salicylic acid. And you might be asking, well, why would we use acetic anhydride, meaning the starting material, rather than something like the acid chloride derivative? Well, the reality is it's a lot harder to work with acid halides because they're more temperamental to things like water. They're harder to work with, they're more expensive, they're more hazardous. Anhydrides are a lot more gentle than acid chlorides, and they work well in these sorts of applications. All right, so it's pretty interesting. As you can see, the reactivity that we just showed here shows a really similar pathway through which your nucleophile will attack in, and then you've got some sort of leaving group. In this case, this half of the anhydride is going to be kicked off as our leaving group. And it's important to remember you have to go through a tetrahedral intermediate, as I've got shown here. You don't want to show it as a straight SN2 reaction. All right, luckily, all of the reactivity more or less is very similar to what we saw in the acid chloride chapter. So let's just jump in and make a reaction map, and we'll try to remember all of the similar reactivity that we saw in the acid halide chapter. All right, and just like before, I'm going to have my acid on the left, meaning my carboxylic acid. I'm going to put my anhydride in the middle. I'm going to put an amide over here. And in this case, it's going to be a wide variety of amides. I'm just going to keep it generic right now. We'll have an ester down here. We'll have an aldehyde right here. We'll have a tertiary alcohol over here. We'll have a ketone down here. And I think that more or less should do it. All right, so let's first do our interconversion between our carboxylic acid and our ester. The first thing that you do need to think about is we need to form our carboxylate by ripping off that proton. So what I would do is use some sort of base, in this case sodium hydroxide would work well, to deprotonate. That gives us our carboxylate salt. And then in step 2, we need to add on this whole half, right? And we said that that could be done by using our acid chloride. So we could add in our acid chloride. Chloride will fall off as our leaving group, and we can get our anhydride. Conversely, if we want to do the reverse reaction, all we really need to do is to react this with water. It will fall apart slowly, and this works well, especially if you have acid, to ensure, like I said, that this proton is attached on the very end. All right, so we can interconvert really readily that way. If we want to form an amine, what we saw with the acid halides was we want to kick off this entire group, right, and replace it with this NH2 group, which implies that we need some sort of NH3, meaning ammonia, in excess, where it acts as our nucleophile and our base. However, this reaction is really, really slow. It's not very practical because this leaving group right here isn't as good of a leaving group as chloride, so it tends to be a little bit more sluggish. All right, the next one, if we want to form an ester, in fact, let me slide this over a bit more. Just like we did with acid halides, we would need some sort of alcohol. And in this case, we don't need any additional pyridine because we don't have to worry about generating HCl as a byproduct. However, if you want to run this with pyridine, that also works. It's just not required in this case. All right, and if we want to form an aldehyde, just like we saw, we don't want to use a super strong reducing agent or else we'll go straight to a primary alcohol. We need to use a bulky reagent, and in this case, it works the same as with acid halides, which is just one less thing you got to remember. So the lithium tritert-butoxy aluminum hydride works well in this situation. If we want to form a tertiary alcohol, again, we can react this with a Grignard reagent in excess, and that works with any Grignard reagent. It could be a magnesium chloride, magnesium iodide, magnesium bromide, doesn't really matter. However, it runs away uncontrollably, so we react it with excess, and then we quench the reaction with water. If we want to stop at the ketone intermediate, like we saw with our acid chlorides, we need to use a bulkier reagent. In this case, the best reagent that we can use is that organocuprate, specifically the lithium dialkyl cuprate. So that would be R2CuLi, also known as the Gilman reagent, and that will install one alkyl group, but won't overreact and push you all the way to the tertiary alcohol. So as you can see, these reactions are really similar. I'm not going to go through each mechanism because it's really repetitive. They all tend to follow the same reaction pathway shown here, where some nucleophile will attack in, will kick off a carboxylate as a leaving group, and then the carboxylate can facilitate the proton transfer in one of our last steps. All right, good luck studying.